All right, welcome back. Continuing this thread of particle systems. Now, the previous examples, we just have these local things that make local decisions and they kind of go away. That's fine, but they can actually communicate while they're at it. So particles, they can communicate with each other. Why shouldn't you say it like that? Particles can communicate. Particles can... They can survey. They can survey the scene. They can look around and go, who's close to me? Who's far away from me? Okay? They can interact with each other. They can make group decisions. So if we overlay more ability on top of this particle system, the complexity and the capabilities just keep growing. Make group decisions. Okay, something is not working with my pen. Let's try decisions. All right. Okay. So, as I've said before, the whole point here is we want to make these complicated systems without having to do this global modeling. So let's look at an example here. I'm going to give a demo, demo 13. I knew that was coming. That was kind of acting funny. Help. Herc. Okay. Does that look about right? It's a bit big. So, back to where we started. I'm going to jump into demo number 13. So, what we have here, this is again another processing implementation. I didn't make this, but this is implementing a flock using the classic Boyd's algorithm. The same pattern we just saw. We have a setup, we create a new flock, we add a bunch of particles. They're called Boyds, which is like a bird. In this case, we're adding them all at the center of the screen, 0, 0, and then each draw, where's draw? We just tell our flock to run. We have a flock, which is a particle system. It's in a list of Boyds. Each run, we tell each Boyd to run. We add one, we add one. No big deal. Then the Boyd class, I'm not going to get into this, but the Boyd algorithm is a classic algorithm. You have particles that look around itself, look at the neighbors, and it tries to solve 3 things simultaneously. Let me see if I can find it for you. It tries to separate. It tries not to collide with its neighbors. Not always possible, but it tries to move away from its immediate neighbors. It tries to align with its neighbors. If the neighbors are going that way, you move a little bit towards them, okay? And if you're moving in opposite directions, you'll eventually come together and move in the same alignment. You try to align with your neighbor. And you try to be cohesive with your neighbor. So we don't want to collide, but if I'm far away, I come close. So 3 rules, right? I approach my buddies, but don't collide with my buddies, and try to stay in a similar direction of my buddies. What's going to happen? I have these 3 rules. I solve them locally. Each particle solves them. All the math is in there. There's stuff to wrap around the screen, that kind of stuff. Make sure I don't go too fast, that kind of stuff. But it's not that bad of an algorithm. So 263 lines. What's going to happen? Let's run it. Cool. Look, we have a flocking algorithm. Now I can actually click and add more and see what happens. But because it's a particle system, each one maintains their own agenda. But look at the resulting behavior. This is really complex looking. This is exactly what we saw in the Batman and the Lion King. This is the kind of flocking behavior. Now, the problem with these systems is if it doesn't quite act the way you want, it can be hard to control because it's an emergent behavior, which is kind of a black box. All we can do is tweak these parameters at the bottom. So I'm going to play with a couple of parameters. The first thing I want to show you is instead of starting at 0, 0, what if we started them at a random location? Would they come together? Would they flock? How would it work? So if I start them at a random location, you get these local flocks coming. But eventually, because of the cohesion property, eventually they'll move together into one cohesive flock. You get this really, really complicated flocking behavior. How cool is that? The other parameter I want to play with is it has this acceleration where it starts over and restarts this acceleration each time. Don't worry too much about it. It starts over so it can recalculate. I'm going to turn that off. Okay, so it keeps the acceleration, makes it a little less smart. And this is an example of how you change one small little parameter. Each Boyd remembers its acceleration from the previous time. And now, instead of a cohesive bat-like or bird-like or animal-like. It's almost like an insect swarm, right? Look at that. This looks like flies. Again, pretty cool. Big change with small parameter change. And in fact, I'm going to turn off the speed limiter and see, and you'll see again, it'll get even more chaotic. More chaotic is more insect-like, right? There we go. Look at that. That now, and it's getting kind of crazy. But that looks a lot more like, look at them. It's even like hovering around and moving around like a patch of flies would look. And it'll eventually explode because there's no speed limiter. It'll go faster and faster and faster and faster. But you could put a limit. You could imagine putting a speed limit on that's not quite as limiting as the other one, and having more or less organization, less regularness in the algorithm. Okay, so this is really nice. I think it's a really cool example of how just a few lines of code you solve the local problem. All right, find my buddies. Let's be cohesive. Don't bump into my buddy. Let's steer away, and let's try to move in the same direction. You get this really advanced behavior coming out of it. Now I'm going to go back to my iPad real quick. I'm going to write out something I've been saying all the time because I think it's really important to have in the notes. So typically, the whole point of particle systems is that they enable this bottom-up thinking. They enable bottom-up solutions or creation of complex systems. It's usually much simpler than a top-down model approach. Think about this Boyd's algorithm, just a few hundred lines of code. If you had to model how you think the animal should move and have this mathematical organization, it gets complicated quickly. This bottom-up solution is really quite simple. Now, before I'm done with particle systems, I want to show a few slides. This is, you can take this really far. Here are some examples of particle systems. Smoke is a common one, like I mentioned. You can have these smoke effects where the density of particles can tell you the alpha value. Fire, explosions, plasma, electricity. These are things that are solvable really nicely with particle systems. If you try to do it top down, it gets really complicated. And I wanted to show this video if it works. Now, I want to highlight in the corner. It says this particle system has 10 to 32 million particles. So this is probably not real-time rendered. But look at that. How awesome. Look at that. Dissolving particle shapes. Doesn't that make you want to get into graphics? Right? Particle systems are really cool. You can solve really complicated things top down, bottom up, instead of having to think about modeling them top down. All right, so thank you. This is the end of particle systems. We'll come back and learn a bit more about animation.